Welcome everybody. We're right 1 minute past our start time. My name is Carolyn Jacobs. I'm with WGBH Education, and we just ran a short clip that I'll be referencing later on in the session, just a way to kind of warm up for those of you who were able to log on earlier. Welcome, and thank you for joining us. If you'd like to introduce yourselves in the chat box, feel free to do so. We're asking all of you, the attendees, to chat with your colleagues and with the presenter through the chat box rather than the microphone. And if you have called in, and I think just maybe a couple of you have, just please mute your line using *6 so we don't hear any feedback. We are recording, and we'll be sending out the recording link to everyone who registered probably tomorrow, if not tomorrow, certainly by Monday. And we'll also do a quick recap of a lot of the URLs that we reference. I know it's going to move pretty quickly, and we have lots of information to share. And so we try and recap things and put URLs together in a Google Doc and pass that along. And we'll do that and send that out to you. This session is sponsored by WGBH and PBS LearningMedia. PBS LearningMedia is a free website, and it's a joint production of PBS and WGBH, which is Boston's PBS station. It's a supplemental digital resource library of over 150,000 resources, some of which are drawn from programs that you see on public television. For example, NOVA. You will find on the website short clips, typically 3 to 5 minutes, that are drawn from NOVA programs. And of course, NOVA is produced here in Boston at WGBH. If you haven't already signed into the site or explored it, we encourage you to do so. And we'll be referencing resources that you find on there. Lisa Sama is our featured presenter, and she has been teaching engineering for 14 years, currently teaches grades 5 to 8 at the Luther Burbank Middle School in Lancaster, Massachusetts, where she founded the engineering program. She's been coaching a First Lego League robotics team for 10 years. She introduced the district's first a 3D printer into the curriculum, and recently she kicked off a maker space at her school, which she has full intentions of expanding in years to come. In her spare time, she mentors tech engineering students at her alma mater, Fitchburg State University, where she earned a master's degree in tech engineering. And outside of education, she sings in a choir, she wins awards in photography, and she enjoys museum hopping, so a very busy lady. And welcome, Lisa. We have had a great time planning this webinar. It's been good to get to know you. Hopefully sometime I'll meet you in person. And thanks so much for working with us. Okay, you can go ahead, Lisa.
Okay, hi everybody. I'm Lisa Sama, and as Carolyn mentioned, I am the tech engineering teacher at the Luther Burbank Middle School in Lancaster, Massachusetts. And it's a very small town, so the way we run our classes is I see the 5th grade once every 6 days, and then I see all of the middle schoolers twice in a 6-day rotation, and I see them all year. We don't split up our specials in trimesters or anything like that. So, and I like teaching like that. I like seeing all the students, and I like seeing all of them all the time. So one of the things that I do is I am in Massachusetts, we have standardized testing, and so engineering happens to be part of that science standardized testing. So I use the frameworks, the Massachusetts frameworks, to help guide my curriculum. And now we are doing, Massachusetts has adapted the NGSS standards. And so this year, engineering and 6th grade science started with the new implementation. I worked with the 2 engineering teachers from the other 2 towns in my district, which are Bolton and Stowe. and we came up with several new lessons for the 6th grade. One being something, a middle school program from the Museum of Science on Mount Everest, and another one also Museum of Science. We did engineering as elementary, the circuits unit. As far as best practices go, you can see the best practices slide right here. We are implementing our best practices as job-alike teachers. We get together every so often during the trimester for professional development, and what they do in my district is all of the engineering teachers from grades 6 through 12 get together and try to outline what our best practices are, and the science teachers also, job-alike grade levels, do the exact same thing. So I want to say welcome. This is my first time doing a webinar. I'm a little nervous, but I'm going to go for it. So I just want you to look at the best practices. These are the best practices from NGSS, and I will be referring to them throughout the webinar as far as which of these I use for the 2 particular units that I'm going to show you this evening. First of all, this slide might be familiar to a lot of you, especially the engineering teachers. In an engineering class, we always follow the engineering design process, always. And it's changed throughout the years. This looks a little different from when I first started teaching engineering 14 years ago, but it's still the same. In other words, all the steps are still the same. You still have to go through this process to figure out or to try to solve your problem. And in my classroom, basically, we always begin with the engineering design process, and I always begin by identifying what the problem is. So in this particular unit that we're going to talk about right now, this unit is about building bridges. And in Massachusetts, the Department of Elementary and Secondary Education, bridges is one of our standards, and in fact, even with the adaptation of NGSS, we're still doing structures, and that includes bridges as well. So the way that I will begin this unit is I'll say to the children, okay, we're going to start. You're going to make 3 bridges. You're going to make a beam bridge, an arch bridge, and a suspension bridge. But first, before I give you all the material so you can begin, you need to do this correctly, and you need the resources to do it correctly. And so we begin then the research step in the engineering design process. That step consists of notes that I have put in a presentation, and I still do it the old-fashioned way where I still ask students to write down their notes, because again, I do believe that when you write, you remember it, and certainly helped me get through graduate school by writing down and outlining chapters. So I'm lucky in that I have a smart board in my classroom connected to my computer, so that what I can do is I can put together not only words, but I can also add film, and I can take things from different websites quite easily with my smart board. So anyway, we're going to begin my bridge building unit, and I tell the students that this is a unit in civil engineering, and we'll talk a little bit later about what a civil engineer does. And as you can see, I've used this picture here of the Brooklyn Bridge, which actually is my favorite bridge, and I love the story behind it, but that's for another time. So I'm going to move on. So the first thing that we have to do before we even begin to talk about bridge building is the students need to know about what forces act on what structures. So if you look at this screenshot right here, the one that says structural forces, what I've done here is I have written these notes up for the children, so this is part of my presentation. And what I did right here is I put a little reference to this wonderful forces lab that is on the PBS Learning site. And it is part of this wonderful series that PBS did several years ago with David Macaulay called Building Big. And again, I can talk a little bit about that later as well. But I want to show you this website, or this Forces Lab. So the children will do things like they'll write down a definition. And then it's nice to write it down, but then I like them to be able to see it. So one of the things that I will do is I will go to this website right here and show it to them. So I'm going to do that right now. I'm going to share my screen. Okay. And I'm going to go to the Forces Lab right here. Can everybody see that?
Yes.
Caroline, can you see that?
Lisa. Yes,
All
I
right.
can.
So,
good.
So what I do is I'll have the students write down, let's say, one definition. We'll start with squeezing. And then I'll come into this lab and I will click this and I'll actually show them what squeezing looks like. And it gives a nice definition here again of compression is the force that squeezes the material together. And I ask the children, what do you notice about the material? And they usually all say, oh, we can see that it's actually getting smaller. And in real life, PBS has put these pictures in. These are construction workers working on a skyscraper. And I mentioned that you can see the workers, you can see equipment up here. And what you'll notice is that it is actually pushing down, squeezing on this floor. And then normally I would go back to my slideshow so we could do the next definition, which would be tension. And again, if you look, you can move this. And actually, I don't know if you can hear the sound, but it makes a really cool sound, and the students really like that. And again, the students notice that with tension, the material becomes a little bit bigger. And in real life, we're looking at the Brooklyn Bridge, and I talked to the students about how the cables of this bridge are in tension, meaning that they are being stretched as the live load is walking across it. We also discussed bending, which is tension and compression at the same time, and I show them this video, or this photograph, excuse me, where they're going to see that there is stretching at the top and there is some squeezing at the bottom. And if I go back, I can actually show you. We also will talk about things like when civil engineers have to build in places where there are natural disasters, like if they're building on a fault, they have to be concerned about the force of shear. And I show them what shear looks like. And it's materials that are sliding apart, or sliding, excuse me, in opposite directions. And I show them in real life what it can look like. And I'm not really sure where this photograph is taken, but I always assumed it was maybe taken after an earthquake, where we can see that the materials have slid apart over here. And we talk about, we also talk about twisting or torsion, which, and I will talk to them about building in a high wind area or areas that are prone to tornadoes, show them what torsion looks like. And then in real life, this is actually another one of my favorite pictures, is Galloping Gertie. This bridge was built in 1940 in Seattle, and I'm sorry, in Tacoma, Washington. And within a month, or 4 months or something like that, because it was not well constructed, the wind collapsed it, and it took 10 years for them to rebuild it. And actually on YouTube, you can find the actual video, and I do show that to the students, and they really like that. So I'm going to go back to the slideshow. And so, Caroline, I just hit slides up here.
Yes, go to slides, please.
Okay. Okay. So once we finish with forces and we finish with this lab, I go off to the next piece of information here. I think it's also important for students to understand what a civil engineer does. And again, from the PBS Learning Media, this clip, it's called "It's Cool to Be an Engineer," and if you don't know it, you can always go onto the PBS Learning site and you can do a search for it. I really like this video, and what I'm going to do is I'm going to show it and then explain to you while it's on why I really like this video. Okay, so I'm going to close this. Here we go. Okay, and here we are. And Caroline, you can see it. Caroline, you can see it okay?
Oh, yeah. Thank you. Mm-hmm.
Okay. This is also, I believe, part of that TV series that PBS did with David Macaulay called Building Big. And this is part of the reason why I like to show this video. This man who is a civil engineer is a man of color. He's also an immigrant. There's a woman. And I think it's really important for students to see, particularly our female students, to see that not all engineers are white American men, that they are people from different countries, they are people of color, they are women, and they're all doing this wonderful job of building all these great structures for us. Carolyn, do you want me to show the entire video or?
No, I think that's enough. Yeah, Lisa, thank you.
Okay. So we'll go back.
It's about it's a 3-minute clip. Mm-hmm.
Right.
And then just click back on the slides.
Yep, there we go.
Great. You're getting pretty good at this, Lisa.
Thanks. David Macaulay, I don't know if any of you have know about this series. It is a wonderful series. You can also get a whole set of DVDs from PBS. David Macaulay also wrote the book Building Big, and I had the pleasure of attending a seminar of his at the Courier Museum in Manchester, New Hampshire several years ago. And he not only gave a wonderful speech, but he signed books afterwards. So I bought a copy of his book, and he not only signed it, but he drew a woolly mammoth in it for me. So it's one of my most treasured books. So after we have talked about what a civil engineer does and the forces that affect all structures, we move into bridges. So we take notes about the different types of bridges, or the students take notes, and the notes will include information about location, about span, about resources, and about live loads and dead loads. So we begin with the simplest type of bridge, which is our beam bridge. Now, these are the notes that I make them write, and these are this is information that I have collected. And then what I will do after we take down the information, I will show them this picture from, again, PBS Learning with a picture of an elephant on a bridge, and we talk about the force of bending. And the students will see that there is the squeezing at the top of the beam, and there is the pulling at the bottom of the beam. But in addition to that, we talk about different types of beam bridges. This is a basic, simple beam bridge, but there are others as well. And there are cantilever bridges and there are truss bridges. And again, if you notice this little icon, both of these icons here, these are actually links to, again, the PBS Learning Media site, where I show them film clips of cantilevers and a film clip of a truss bridge. So I'm not going to show both of them, but I will share with you the cantilever bridge video. And this bridge here is the famous Firth of Forth Bridge in Scotland, and actually it's on my bucket list. I'm having a little trouble here showing this one, Carolyn.
If you just click on the arrow there on the, yep.
There we go. No, I'm back in
No.
slides.
Okay,
I'll go back to
Lisa,
cantilever.
yeah, try it again. And if
Yeah,
you
what
click
I've
on
got
the,
is a black screen. I've
yeah,
got a black
but
screen.
you have to press the start, the arrow at the bottom left-hand corner.
The fourth bridge is a cantilever bridge.
Let me do it.
Okay.
And although it looks quite complicated, the principle is really fairly straightforward.
Sorry.
And everybody can
People
hear it
came
through
from
their
miles
computer,
around to
Lisa,
hear
so
Baker
we,
explain it, using his assistants as human cantilevers. The men in the chairs
That man that was
represent the
drawing the
towers
picture
from
was a
base
young
to top.
David Macaulay. He doesn't quite look like
The
that
diagonal
anymore.
sticks are the thick steel tubes projecting
And
from
this
the base.
clip illustrates how a
Their arms
cantilever
are the
works
steel limbs
and
hanging
also
from
how
the
the
top.
forces of tension and compression act on that bridge
With the bottom
to help
members
it
in
support
compression
both its
and top
live
members
load
in
and
tension,
its dead load.
the cantilevers support the connecting roadway that the third man sits on.
And Carolyn, do you want me to show the rest
Each
of it,
main
or should I
section is
stop
also
it?
firmly
I think you
secured
can
at the
stop
ends
it, yep.
to
Everyone
provide
got
additional.
a taste for it, and we're going to make sure they know where to find it.
Great. And the truss bridge one is actually quite good too, and it talks about trusses in beam bridges and how they got started in America. They were actually basically patterned off Gustav Eiffel's truss bridges in Europe, and that they were bridges that the railroad started using to eliminate a lot of the railroad disasters that they were having on the old bridges. Another thing I do with beam bridges is I show lots and lots of pictures. So on the left, you'll see a beam bridge that is spanning a small body of water. And for added strength, I point out to the students that engineers will often add columns underneath it. And the students will need to know this later when they carry out their own investigations and they write their lab report. Now on this side is a truss beam. And again, I point out that it's over a longer body of water. And again, engineers have chosen to use more columns to keep it for added strength. And this one is a simple one. And notice that there are no added columns underneath it. Over here, another picture I show them. I ask the students actually to draw and to label all the parts of this beam bridge in their notebooks. And they use the slide on the left. This one right here is their guide. And again, when they carry out their own investigations and they write their lab reports, they're going to need to be able to describe accurately what force they saw and where they saw it. And this is why it's important for them to learn this vocabulary. And again, I show them another bridge with more columns for added strength. Pictures are great. I show lots and lots of them. Once we finish with our beam bridge, we move on to the next kind of bridge, which is arch. And again, these are my notes that I give them about arch bridges. And again, I go to the PBS LearningMedia, and we take a look at this picture right here. Students are learning that the arch gets stronger the more weight that's put on it or around it. And if you look in this picture, it's not only showing the force of compression around the arch, but it's also showing the buttresses on the sides and how they are also compressing the arch. Now, my favorite video is this one. This is also a great video, and David Macaulay is also going to draw a picture for us, so I'm going to show you that one now.
Wherever they could, the Romans constructed their bridges out of stone. Though stone is more difficult to work with than wood, it's stronger, needs far less maintenance, and is an excellent material for building arches.
Thank you.
Now, what's special about
in
an
this
arch?
video here,
Well,
he's
just look at the
showing us
alternative.
some of the famous
The simplest way to
arch
span a
bridges
river or
in
valley
Rome.
is
And
with a
then right
simple
here
post
he
and beam
draws it.
arrangement.
And he
Vertical wooden
also,
posts
I'll let you
set
see it.
fairly close together to support a horizontal roadway. By building stone arches like the ones behind me, the Romans were able to span the same and even greater distances while minimizing the number of obstacles to the river's flow and to ship traffic. But what keeps an arch from falling down? The answer is its shape and the weight of the bridge above it. Here, let me show you.
So in
Wedge-shaped
he's going to
stones
show
are
the
laid side by side in a semicircle.
That make up the
They
arch.
are initially kept in place by a wooden form until they are locked together at the top with a keystone.
This is the form that they build the arch bridge over.
By itself, a stone arch can support very little.
All together.
And if you add weight to the top, the sides will start pushing outward and crumble. So the Romans placed stones around the arch to counteract this outward thrust.
So, Carolyn, do you think it's okay if I shut it down now?
The weight at the top serves to press the individual arch stones together, making the entire
help hold the arch together. Okay. And again, I always have lots and lots of pictures, and not only that, but another picture illustrating the parts of the structure. And again, the students have to draw this in their notebooks, and they have to label it. And I also show them pictures of arches that are under the bridge and an arch that is over the bridge, so they understand that the arch bridge can look both ways. And lastly, we talk about suspension bridges. And again, students take down these notes from my slideshow, and I go to the Building Big site, or the Building Big information on PBS Media, and I show them this bridge, and we look at the columns being in compression, and we look at the cables being in tension. And again, I illustrate two different types of bridges. The Golden Gate Bridge is a classic suspension bridge. This bridge here on the right is the newer type of suspension bridges that we're building now in America. They're called cable-stayed bridges. But in Massachusetts, I don't know about other states, but in Massachusetts, the Department of Elementary and Secondary Education classifies it as suspension for testing purposes. And also vocabulary. It's really important to me that students know the vocabulary. I can't stand when students come up and talk about things. They say this thing. I hate that. So I make them learn the vocabulary, and I make them tell me the actual words when they want to ask a question about something. So before we build our bridges, one of the other things they have to learn is the difference between a live load and a dead load. And again, I'm going to just show you this lab really quickly. This one comes from the Building Big area on the PBS LearningMedia. I'm going to share my screen. And let's go Loads Lab. Right here. And I won't show all of this, but in Massachusetts, students need to know the difference between a live load and a dead load. So we talk about the dead load, being the weight of the structure. And we talk about the live load being the weight of the objects. And what I like about this lab is that the students actually get to see what happens if you put too much live load on a structure and how you can strengthen it. And again, they're going to need to know this because they're going to be making bridges pretty soon, and they're going to be doing a lab report. And I ask them questions about how they can make certain bridges stronger. So this actually helps reinforce it. And I'm going to go back to the slideshow. There we go. Okay. And another thing I have them do before I give them the challenge is, again, another interactive challenge on PBS LearningMedia is this bridge challenge where students are given 4 locations and they have to figure out what the best bridge is for each location. They do this on their own, on their Chromebooks, and I think it really helps when we actually get into the workshop and start doing our activity. So where do I get the activity? Well, I used to do the old-fashioned, we're going to make a truss beam bridge out of balsa wood, and then we're going to put a lot of weight on it and see how much weight it will hold. What was nice about that was that, you know, we got to break bridges. That was kind of fun, but what was really not so nice about that is students were only able to observe one type of bridge, having weight put on it and observing the load on that type of bridge. And we didn't do anything with arch bridges, and we didn't do anything with suspension bridges. So I found this activity on another website I use that's called teachengineering.org. It's also a very valuable website to anybody, that really to any STEM teacher. If you're looking for any type of quick activity, you can find it on this website. And in addition to that, you can use things from PBS LearningMedia to enhance your presentation. So in this activity, this is now the third part of the engineering design process where they're actually going to start to do their designs. So students are given 3 different scenarios. And what they have to do is they have to make each of the different types of bridges, and then eventually they're going to figure out which bridge goes in which area. And as far as best practices are concerned, this would be asking questions and defining problems. So the first thing the students do in the engineering design process is I give them some graph paper and I have them draw the arch and the arch road, the beam bridge, and the suspension bridge, and all the dimensions are given in the activity. We also do this in feet and inches because my understanding is in the construction industry in America, they're still using feet and inches. So I usually use metric, but in this case, it's feet and inches. So again, we're now developing our models, and that would be our best science practice. So the materials for this activity are right here, and they're very inexpensive. Most of these you can buy on Amazon.com, or you can go to any of the art suppliers' websites. You can go to the supermarket for some of them. And let me see. So this is what the bridges end up looking like. So this is a beam bridge. Students will cut out their templates, and they'll trace them onto the cork that I give them. And with toothpicks, they'll make a beam bridge. The first thing they'll do is they will weigh their live load. I'm sorry, I'll say that again. They'll weigh their dead load, and they'll write information in a data table in their notebook. Then they're going to put the bridge in a piece of styrofoam. The styrofoam represents the road. They then pile it with these washers until they see the force of bending. And I hope on this picture you can all see this bridge bending. And then they take the load off, they weigh that load, just the live load, and then they figure out their bridge efficiencies. And here you can see some students making some suspension bridges here and here, okay? And again, our best science practices, there's a lot of them with this activity. They're planning and carrying out investigations. They're analyzing and interpreting data. They're using math and computational thinking. They're constructing explanations and designing solutions. They're engaging in arguments and evidence, and they're obtaining, evaluating, and obtaining information. So the next thing that happens is they get their lab report. They put in their lab reports. They identify the problem in their lab reports. They list their materials. They list their data tables for all 3 bridges. And then they tell me which bridge belongs in which area and why. So, Carolyn, do you think it's okay now to go to American Experience?
Yeah, sure, thank you. And then while I'm doing that, Lisa, you might flip through the chat box. Lots of good comments and a couple of questions for you also.
Okay.
Do you want to introduce this, and then we'll switch?
Yeah, let me do this. Mm-hmm. So I had the pleasure of actually watching this last week with my daughter, and it's a wonderful. It's wonderful. And so I recently decided to do a new unit with grade 6. And since Massachusetts is now adapting NGSS standards, we've changed them this year for 6th grade. And the 6th grade standards for engineering now are mostly about tools and materials. And so recently I started to get interested in circuitry, especially now that I'm trying to do this maker table at school. I've been doing a lot of things with LED lights and conductivity tape, which I love, and batteries. So I decided to do a circuitry unit with grade 6, and I think it ties in rather nicely with the Tesla American experience. And I hope you all get a chance to watch this because it's wonderful. So I will now turn the webinar over to Carolyn.
Great. Thank you, Lisa. And again, lots of comments in the chat box and lots of suggestions of other resources. I don't think I can actually send the document, which is pretty dense, of a transcript of the chat. So what I typically do, and that's why it takes a little time, is I pull out URLs and pertinent comments that people make, and I include them in kind of a recap that we will send as a follow-up email along with the recorded link. So I hope that that will help you out. So yes, as Lisa mentioned, American Experience recently broadcast Tesla, which was a one-episode broadcast. It was a full-hour program. I think it was broadcast last fall. And what often happens with programs that are broadcast on public television when they have an educational value, the education department at GBH works with the major brand, American Experience or Nova or Frontline or whatever, and we create educational resources that are derived from that program, and we make them available on PBS LearningMedia, free of course, and we often are able to, we say we contextualize them, or we offer support materials, so we're not just offering the media for you, but also some suggestions of how to use it. So we're going to watch a little bit of this clip, and these, there are 3 resources that were just published last night. I'm dead serious about this. It was probably about 9 o'clock when I got an email saying they were all live on the site. And so you really are the first group to see them. And the first one explores the difference between DC and alternating current, which of course was work that Tesla was very involved in. And this video includes an animation, and we learn how Tesla's experiments led him to create the very first efficient AC motor, which allowed electricity to travel distances away from a generator, which was something that had baffled Edison. Tesla came to the U.S. from Croatia with an introductory letter to Edison, and you'll learn about that in the documentary. And he came with the vision and the plan of this AC motor. And of course, that invention led to a whole transformation of life in the 20th century. So I'm going to play just a little bit of this clip and then come back on.
In 1891, a Serbian scientist demonstrated his latest inventions before an awestruck audience at Columbia University. Tubes held in the hand of Mr. Tesla, a reporter wrote, appeared like a luminous sword in the hand of an archangel representing justice. Nikola Tesla was already famous, the scientist whose experiments with electricity were destined to transform daily life in the 20th century.
We live in an electrical world. We take it all for granted. We have light bulbs, we run our refrigerators, our air conditioners, our electrical motors. All of that is all directly back to Tesla.
Tesla had begun to explore the possibility of transmitting energy without wires. Here is a simple glass tube, he told his astonished audience. Wherever I move.
Hi, I'm going to stop this here only because for some reason my videos are not labeled correctly, and this was not exactly the first one I wanted to show. But that's okay. You get a taste for it, and this is another clip that's available on the site. This one is showing Tesla's experiments with wireless electricity. I also want to show you an example of what those resources look like for the teaching tips and the vocabulary. So I'm just going to pull up a PDF document here. So this is a teaching tips, and you find this on the website under the media. They're in the support materials. And in this case, we are laying out the essential questions and then also viewing prompts and discussion questions for before, during, and after viewing the video clips. And these teaching tips are created by teachers, actually, and are content experts, and we get very good feedback from them. All right, I'm just going back to the slides again, and yeah, this is, there's also a vocabulary handout, and we have 2 of those on these brand new resources. This is the video clip that I'm not going to play now. This is one I showed prior to us starting, and this is part of the resources that were just launched last night. And this shows how Tesla's work 100 years ago is really informing the research that's going on now to allow us to charge all of our devices without the benefit of wires. Wouldn't that be wonderful? And then there's also another video clip showing Tesla's not so successful work in exploring wireless power and electricity traveling long distances. And just for the heck of it, I mentioned that my videos are mislabeled. I'm going to play this one for a second and see if I've got the right one here. Hold on. Maybe this is going to be the ACDC.
Beneath the ground ran 80,000 feet of copper conductors, the world's first electric grid. Thomas Edison's creation, lighting homes and powering factories on the lower tip of Manhattan. But Edison's system generated direct current, DC, and DC had severe limitations.
Direct current couldn't go very far. You would have had to have a generating station every mile. It was a very limited form of power. So this was a real problem, and Tesla had the solution, a brilliant solution.
With direct current, a generator produces electricity, a stream of electrons that flows along a wire to a light bulb or a motor, and then returns to the generator in one long continuous loop. But as the electrons travel, energy is lost to the resistance of the wire. The alternative to DC is AC, alternating current. With alternating current, the electrons don't flow in a single direction.
Okay, I'm going to stop it there. I think you get the idea. I think it's wonderful. This animation is included in the show. I believe. I think I saw it in the show also. And we're very proud to be able to take short segments of such high-quality broadcast and make them available to teachers. We know that you may not have the benefit of time to show an entire program, and it may not even be appropriate, but these short clips are where it's happening. So, all right, so in the email you will get from us, we will give you the links to these, but if you go on PBS Learning Media and just put in Tesla in the search box, you'll find quite a bit. You'll also find references to all of the Edison work. American Experience had a broadcast about Edison several years ago.
Yeah.
And actually not several years ago, it was pretty recently. And there's a lot about Edison also. Okay, so Lisa is going to quickly go through what she's working on now, circuitry, and then I'm going to come back on and wind us up. Thank you.
Okay, I'll be quick. So this is my new thing. I really like circuitry and LED lights and conductivity tape and all that fun stuff. So the other two tech ed teachers in my district, when we got together, we decided to do a unit using circuitry. So I'll go through it quickly. That's just another copy of the engineering design process. So again, I borrowed a little bit from Engineering is Elementary, and then I borrowed some from this website is another good one called tryengineering.org. And so this website right here, Try Engineering, I mean, everything is geared basically for elementary through high school, and you as the teacher just, edit it for your own personal needs. My students, I wanted them first to prove to me that they knew how to make a simple circuit. So I used the information from this book for them to make and prove that they knew how to do it. That was part one. Part two was I wanted to make sure that they knew the difference between an insulator and a conductor. So what I ended up doing was putting out all these materials, and students picked 5 materials that they thought were insulators and 5 that they thought were conductors, and they tested them to make sure that they were correct. And then we came together and we shared our findings. Finally, I wrote a problem here where this woman is really frazzled and she forgets to feed her cat who has special needs, and so she wanted to set up a kind of an alarm system so that when she got home, if the cat's food bowl was empty, she would see a light bulb shining. So like I said, the first thing I had the students do was I had them show me that they knew how to make a simple circuit, because you never assume prior knowledge. And interestingly, some knew and some didn't. So it's good to start at the beginning. Most of this stuff I bought through Amazon.com, and it was really inexpensive, and it comes in like one day. And then the next part of it was I gave them a worksheet, and they had to pick 5 materials that they thought would be conductors and 5 that they thought would be insulators. I put out all different kinds of material, like hair clips and aluminum foil, and I put out some steel ball bearings, but then I put out things like marbles and paper and pencils and things that I knew would not conduct electricity. And the students actually did a really good job of figuring out which conducted and which didn't. And now comes the part where I give them the third part of the problem about the woman who needs to make sure her cat gets fed, and the students working in teams of 2 made these switches, just prototypes. This right here represented the cat bowl, and they made like a lever type thing, so we got to talk about simple machines as well. And they are now just conducting experiments with the different conductors and some of the other materials. I gave them the batteries and the alligator clips and the light bulbs. And they were just, for about 2 classes, I let them practice and test until finally they had themselves a working switch. And here's some more students working, and this girl right here wanted me to tell all of you that she's my favorite student, so I told her I would. And then over here is another example of what some of them did. Since this was my first year doing it, I kept it really simple, but for next year I'm going to add a couple more components. I'm going to let the kids be a little more creative with their switches, and also try to come up with a switch that falls on in the same place every single time. When they were testing them, they kind of had to move them over a little bit. And again, it was my first year doing it, so I will refine it again for next year. Okay, so I'm going to turn the presentation back over to Carolyn.
Wow, thank you, Lisa, very much. Again, good comments in the chat box, and you can scroll through and see what people are talking about. Yeah, okay, well, we are winding down. I wanted to just remind you that pbslearningmedia.org is a free site. We have over 150,000 resources on it now. More are being published all the time. There is a Massachusetts version, so when you log in with your Massachusetts zip code, you will be redirected to a homepage that looks like this where we post some local announcements. But all of the content is available nationally. And of course, everything is aligned to the Massachusetts standards, NGSS, and the Massachusetts state standards also. On the site, you will find short clips, often 2 to 4 minutes, 3 to 5 minutes, interactive activities, student self-paced modules, which we're producing a lot of, and that's for another time. Lesson plans, they always include media, very detailed, not designed for you to follow totally, but pull pieces out, and we always show you when it's appropriate to run the media. Thousands of images, so it's safe for your students to go on the site themselves and find images. The credit, citing them is very easy to do, downloading them, etc. Audio files and professional development. As you would expect on a site that has lots and lots of content, we try and make it as easy as possible for you to search and find what you're looking for, save it into folders, share your folders, and through relatively new teacher tools, you're able to create your own video-based quizzes, storyboards, puzzles, etc. We try very hard to make everything available for download, knowing that that is necessary with many teachers. Sometimes it's not possible because of clearing the rights issues, which is expensive and time-consuming, but we do our best. And again, the resources are all aligned to standards. One of the easiest ways to search the site and start to become familiar is to choose to search by collections. And collections are an easy way to find a group of individual resources that are all related to the same topic or connected in some way. So these collections, these are just examples. There are hundreds of them. These are examples for elementary, kind of related to the topic that we're talking about tonight. So I'm sure that some of you remember the old Zoom program, and some of those Zoom clips are really great for teaching engineering. Plum Landing is a web-based series. It has never been on television. And it's science-related. It's not really engineering. It's more environmental science, but it's very popular and for the elementary grades. For middle school, Design Squad, of course, is produced by WGBH, a very well-known and well-respected resource to teach engineering. Adaptive Technologies is a fascinating collection of videos. It's in collaboration with Design Squad, and it shows teams creating materials that help athletes who have special needs. And it's just wonderful, rewarding, and fascinating. Engineering is Good is a brand new problem-based learning lesson around recycling plastics, and it was just launched. It's gotten rave reviews so far out of KQED in San Francisco, and that's on the site. A couple of examples of collections for high school. Lisa had mentioned that she was familiar with the aerospace engineering collection. Lisa, do you have anything in particular about that collection you wanted to call attention to?
There was something that Boeing had done,
yes.
And I looked at it again the other day, and it actually had some film clips, and it showed the forces of flight and it showed them all. I think it took each one individually, and it did something pretty cool with each one of them. And I thought, I do transportation with my 7th graders, and I thought that would be a good link to put in a Google Classroom for them.
Yeah, yes, it was a collaboration we had with Boeing and the 100-year anniversary of, I guess it was Boeing, I can't remember, it was last year.
Mm-hmm.
And
Yep.
there is an interactive in that also where you actually build your own jetliner and have to take into consideration all the variables. And then there are a series of career profiles of aerospace engineers showing a variety of gender and ethnicity, and it's really very well done. All right, and then for all grades, here are 3 collections that have resources within them or are applicable across all the grade bands. Teaching NGSS Engineering Design Through Media was a project we did with Raytheon a couple of years ago, and if you search that collection, you'll find resource links for all the different grade bands. And then these are 2 other collections not produced by GBH but available on the site that we're very impressed with. The STEM career profiles, yeah, this is an example of one from that Boeing Aerospace Engineering collection. And Tony, I can't remember his last name, but Tony was really bitten by the bug of going into aerospace engineering when he was in Florida with his family, and he watched a launch. And typically in these career profiles, which usually run 2 to 3 minutes, we will show someone, they're usually young and very passionate about their jobs, and they talk about what they're doing and how they got started, what inspired them. And we see pictures of them when they were much younger, and maybe talking about a teacher that turned them on to something or their background. They're really wonderful stories. And we hope that they inspire a new generation of people who follow them. Okay, we're at the end, so I was going to show this one. This is from The Secret Life of Scientists and Engineers, and someone in the chat box mentioned that project. It is a NOVA project. It is available on PBS LearningMedia. These are some of the they're just wonderful. They're so well done, and a whole variety, and there are many of them. Tom Schultz is a music engineer, and some of the people that we profile are kind of characters, which is good, and they are all doing really interesting things. Another favorite of mine is a woman who's a fashion technologist and makes clothing that actually changes color based on the time of day and the temperature. And she's also a snowboarder. A lot of those profiles point people not only to what they're doing in their professional career, but what they do outside of their classroom. I wanted to give a nod, although it's not really directly related to engineering, but certainly to science. This is a project, a 5-year project that GBH has partnered with NASA on, entitled Bringing the Universe to America's Classrooms, and we're in the 2nd year of a 5-year project. We are developing resources for K-12 for earth science using NASA imagery and data. Very interesting work, and some of it has already been launched on LearningMedia, and much more is to come. And we are working with 50 teacher advisors across the grade band and across the country to inform our work. And each year we have a new cohort of teachers, and we're just getting to know this year's cohort now. And part of the project, actually it was last week, we ran a webinar on the solar eclipse, how to teach the solar eclipse. And like this one, we record all of our webinars and offer the recording links for you to watch on your own time. And we also have put together a solar eclipse toolkit. In our work with NASA, it's very important to NASA that people know about the eclipse that's coming August 21st, total eclipse, and that they watch it safely. So lots of resources for you there that you will get in my email. Okay, gosh, 1 minute over time. So thank you very much. Thank you, Lisa. Wonderful.
You're
You would
welcome.
never know that you were a newbie. We got through without too many snags here. Actually, I think my mislabeled video was the worst thing that happened. So I hope that everyone agrees that this was time well spent. We will get back to you in the chat box if we weren't able to get to you in real time. We will keep things open on the chat box for another few minutes, and wish you a lovely evening, and thank you again for joining us. And Lisa, it's been great getting to know you, and I hope we have another chance to work together.
I hope so. Same here. Thank you.